This video, we're going to look at the first type of fragmentation, alpha cleavages. Alpha cleavages are fragmentations that occur at the bond next to the functional group. That position is called the alpha position, so that's why they're called alpha cleavages. For example, if you look at our first case at the bottom here, you can see that if we have a heteroatom that has a lone pair, the alpha cleavage is going to occur. We're going to lose a bond, lose a group that has a bond at the alpha position here, right? So that we are going to obtain this radical in the end. If we have a carbonyl group, for example, something that has a CO bond with a lone pair, a CX bond with a lone pair, we're going to again lose something at the alpha position. So lose this group here to form this thing. And then if we have an alkene, we're going to lose something at the alpha position here of the alkene, so that we're going to form this radical here. So you need to be able to predict where things are going to fall apart, but you also need to be able to draw the mechanism for these reactions. So that's what we're going to be looking at in this section, as the mechanism for this type of fragmentation. Part of what you want to be able to do also is, from the spectrum, you want to be able to recognize where certain fragments come from. And one of the hints that you have that something, a fragment that's observed on a spectrum comes from an alpha cleavage, is this very important observation here, and it's that if you, in an alpha cleavage, if you start with a molecular ion that has an even mass, you're going to lose a radical of odd mass, which means that the fragments that you're going to form are going to be of odd mass. So a very important signature of alpha cleavages is that you start with an even molecular ion and you go to odd fragments on the spectrum. Let's look at some of the things that are involved here. As we said in the previous video, fragmentations occur in order to form the most stable carbocations most of the time. The alpha cleavages reactions are governed by the fact that in all cases here, as is shown in this box right here, we can form resonance stabilized carbocations. So that's why things break up at the positions that we highlighted earlier. That's why we have alpha cleavages for these functional groups. It's because we can form resonance stabilized carbocations. Now, in these fragmentations, not only do we form resonance stabilized carbocations, we also form radicals. These radicals are neutral. Since they are neutral, they are not detected on the mass spectrum. Let's look at the mechanism for these alpha cleavage reactions. A first step is we start from the neutral molecule and we ionize it to form the radical cation. Once we have the radical cation, and it's this one that falls apart, we need to be able to draw arrows for these mechanisms. These mechanisms involve movements of one electron at a time, so we're dealing with homolytic chemistry. If you look at the overall transformation here, what we need to do is we need to form a double bond between X and a carbon, and we need to break this bond here at the alpha position. One way that we can do this when drawing a mechanism would be take the lone electron that's been created in the radical cation and put it on the bond where we want to form the double bond. And then the bond that we want to break, we're going to take one of its electrons and form the double bond with it. And the other electron of this bond that we're trying to break, we're going to put it on the radical. And this gives us directly the carbocation and the radical. So the other two mechanisms on this slide go by exactly the same mechanism. You form the radical cation. Once you have the radical cation, you take the lone electron, you form a new bond with it, and you take one electron of the alpha bond to complete that new bond, and the other electron of this alpha bond ends up on the radical that's leaving. This guy here, the radical that's leaving here. So if we go to our third example, we start by ionizing the alkene to form this species right here. once we have the radical, we can use it to form a double bond. And then we take one electron of the sigma bond that we're breaking, we put it on the double bond, the newly formed double bond, and then the second electron of the sigma bond that we're breaking ends up on the radical here. So make sure that you practice drawing those mechanisms for alpha cleavages. One way that you can practice doing writing these mechanisms, Klein does not have that many problems where you can practice these electron pushing mechanisms, but I posted a handout on fragmentation that has both some explanations and a few problems. Make sure to work through these problems because you need to practice this arrow pushing. In the slides here, then there's a problem where you're going to do just that. Here, let's read the question together. Problem 2, what will the value of m over z for the major fragment of each compound below be? Hint, in each case, the major fragment comes from an alpha cleavage. So we can just look at the first example. We're not going to look at the other 3 on this slide and the next slide together. You'll have to work through that and just look at the solutions on the corrected slides. The first one here is a ketone. From what we saw on the previous slide, we can predict that when we ionize this molecule, there are 2 lone pairs on the oxygen here. When we ionize this molecule, we're going to remove one of the electrons on the oxygen to form a radical cation where a positive charge is on the oxygen. And then from what we saw on the previous slide, we know that this is then going to fragment by an alpha cleavage. And there are 2 different positions where this could fragment, and it's at these 2 positions. Remember that when we do that, the positive charge ends up on the oxygen, so that the part that where the oxygen, the part that the oxygen stays on is the positive charge. The other part is the fragment that is lost and not detected. In this case, this is then what we would predict for this problem. We would predict that the 2 major fragmentations would be cleavages at the alpha position. If we work out the numbers, we see that in a first possible cleavage, we would form a first fragment that has a mass of 85, which is right here on the spectrum. We would lose a mass of 15 that would not be observed because it's a neutral radical. If instead the radical cation breaks on the other side, we would observe a mass of 43. And we would lose a radical of mass 57 that would not be observed on the spectrum. On this slide here, I just show the structure of the main fragments that would be formed through alpha cleavages. You need to be able to just predict those, but you also need to be able to do what's not on this slide, which is to draw the mechanism. So for this problem here, make sure that when you try to answer for each of the 4 molecules, you not only predict what the main fragments are going to be, but you also practice drawing the alpha cleavage mechanisms, and they are shown on the previous slide. So work on your own through problems 1 through molecules 1, 2, 3, and 4. Then look at the corrected slides for the solutions. Okay, so we've looked at one of the main modes of fragmentation, which are alpha cleavages. We're going to take that concept of alpha cleavage and just extend it to alkanes. Alkanes do not have any functional groups per se, so to say that they break, that they fragment at the alpha position is kind of impossible just because there are no functional groups. But we do still use the alpha cleavage nomenclature for this kind of cleavage, just because some of the things that are observed are very, very similar. And one of these things is this guy here, and it's that when alkanes break down by fragmentation, you usually observe that if you start with an even mass molecular ion, you're going to lose a radical of odd mass. So you're going to form a fragment of odd mass, just like the previous alpha cleavages that we saw. And as I said here, then calling these fragmentations when we're dealing with alkanes is a bit of stretched just because there are no alpha positions really in an alkane, but we're still going to use that language. And then the process, the mechanism by which these fragmentations occur is, well, the only thing that we can ionize in an alkane are sigma bonds. So we can remove electrons from sigma bonds. So when we bombard the alkane with high energy electrons, the electrons that are expelled are electrons from sigma bond. So for example, in here we have this molecule as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbon. So we have decane. We blast it with electrons. One electron is expelled, and now we form a radical cation. In this example here, we've ionized this bond. So one of these two electrons has been expelled. So we form this intermediate where there's only one electron in the bond that's right here. We can draw this ionized bond like this, or a drawing that would be just as good would be if we just draw it like this instead. There's really no difference. And then the way that this molecule can fragment, the radical can just leave and end up on the carbon on either side. It doesn't matter. If we look at what's on here, we're trying to explain the base peak at 43. 43 will correspond to a mass of 15, which is CH3, plus 14, which is CH2, plus 14, which is CH2. So 43 corresponds to this mass here. So the way that we obtained this mass of 43 was through the ionization that's shown on this slide, and then through the loss of this neutral radical that for this particular fragmentation will not be observed on the spectrum. With linear alkenes like this, like decane on this slide, there are places where that are more favorable for cleavage, but there's really no driving force. Like, we're not forming carbocations that are much more stable than others, just because the molecule is linear. So that's why you typically see in linear alkane that you basically get all the possibilities in terms of cleavage. So even though the one at 43 is the base peak, you can see that there was also a fragment where we lost one fewer CH2 group. There was another fragment where we lost one fewer CH2 group. And there was also another fragment where we lost one CH2 group. And you can see that all of these are separated by 14 mass units. So it's not a statistical distribution, but all the different possibilities of all the CC bonds are pretty much show up on this spectrum. So this is when we deal with linear alkanes. When we deal with branch alkanes on the next slide, we can expect a slightly different behavior, and it's because with branch alkanes we can form carbocations of different stabilities. So if you just look at the example on this slide, look at this molecule here of 2-methylpentane. Because there's some branching at this position here, we can expect that we can form different carbocations. Just think about breaking the first carbon-carbon bond right here. Then on each side we would have either a CH3 plus or primary carbocation. But if you think about breaking the bonds that are right around the site of branching, we can form, as is shown at the bottom here, we can form much more stable carbocations. If we break this bond right here, we would form a carbocation, a secondary carbocation that's more stable than the previous ones. If we break, instead of this position here, we form another secondary carbocation. Since these two carbocations are more stable, we can expect that for this branched alkane, fragmentation at these positions at the point of branching will be the predominant modes of fragmentations. So we should detect 43 on the spectrum. It is the base ion, and we should detect a 71, which is the second most important fragment for this molecule. So the lesson here is that when you have a branched alkane, yes, you can expect fragmentation at pretty much all the carbon-carbon bonds, but the main peaks are going to be derived from fragmentation at the point of branching, because these lead to more stable carbocations.